I remember the first time I looked in a biochemistry textbook and I saw a drawing of something called a bacterial flagellum with all of its parts in all of its glory. It's had a propeller and the hook region and the drive shaft and the motor and so on. I looked at that and I said, that's an outboard motor. That's designed, that's no chance assemblage of parts.
Behe's reaction was not surprising, for the molecular motors that drive bacteria through liquid each depend upon a system of intricately arranged mechanical parts. These parts come into focus when portions of a cell are magnified 50,000 times. Biochemists have used electron micrographs like this one to identify the parts and three-dimensional structure of the flagellar motor. In the process, they have revealed a marvel of engineering on a miniaturized scale.
Howard Berg at Harvard has labeled it the most efficient machine in the universe. These machines, some of them are running at 100,000 RPMs and are hardwired into a signal transduction or sensory mechanism so that it's getting feedback from the environment.
And even though they're spinning that fast, they can stop on a dime. It only takes a quarter turn for them to stop and shift directions and start spinning 100,000 RPM in the other direction.
And just like outboard motors on motorboats, it has a large number of parts which are necessary for the motor to work.
The bacterial flagellum, 2 gears, forward and reverse, water-cooled, proton motive force. It has a stator, it has a rotor, it has a U-joint, it has a drive shaft, it has a propeller, and they function as these parts of machines. It's not convenient that we give them these names. That's truly their function.
Since its discovery, scientists have tried to understand how a rotary motor could have arisen through natural selection. As yet, they have failed to offer any detailed Darwinian explanation. To see why, we must understand a feature of molecular machines known as irreducible complexity.
Irreducible complexity was coined by Mike Behe in describing these molecular machines. Basically what it says is that you have multi-component parts to any given organelle or system in a cell, all of which are necessary for function. That is, if you remove one part, you lose function of that system.
The idea of irreducible complexity can be illustrated by a familiar, non-biological machine, a mousetrap. The trap is composed of 5 basic pieces: a catch to hold the bait, a strong spring, a thin bent rod called the hammer, a holding bar to secure the hammer in place, and a platform upon which the entire system is mounted. If any one of these parts is missing or defective, the mechanism will not work. All components of this irreducibly complex system must be present simultaneously for the machine to perform its function, catching mice. Irreducible complexity also applies to biological machines, including the bacterial flagellar motor.
All told, there are about 40 different protein parts which are necessary for this machine to work. And if any of those parts are missing, then either you get a flagellum that doesn't work because it's missing the hook or it's missing the drive shaft or whatever, or it doesn't even get built within the cell.
In evolutionary terms, you have to be able to explain how you can build this system gradually when there's no function until you have all those parts in place.
But could Darwin's small, favorable variations have produced a bacterial flagellum? Some scientists doubt the possibility.
How could something new, like a bacterioflagellar motor and all the components that go with it, how could it develop out of a population of bacteria that don't have that system? When each change, according to Darwin's theory, has to provide some kind of advantage.
Imagine such a scenario early in the Earth's history. An evolving bacterium somehow develops a tail and perhaps even the pieces necessary to attach it to the cell wall. Yet without a complete motor assembly, this innovation would provide no advantage to the cell. Instead, the tail would lie immobile and useless, invisible to natural selection, which by definition can only favor changes that aid survival.
The logic of natural selection is very demanding. Unless the flagellum mechanism is completely assembled and actually works, natural selection simply cannot preserve it. It cannot be passed on to the next generation.
The important thing to realize about natural selection is it selects only for a functional advantage. In most cases, natural selection actually eliminates things that have no function or that have a function that harms the organism. So if you had a bacterium with a tail that didn't function as a flagellum, chances are natural selection would eliminate it. The only way you can select for a flagellum is if you have a flagellum that works, and that means you have to have all the pieces of the motor in place to begin with. So natural selection can't get you the bacterial flagellum. It can only work after the flagellum is there and operating.
In 1996, Michael Behe published a book titled Darwin's Black Box. In it, he argued that natural selection, Darwin's designer substitute, could not explain the origin of the bacterial flagellum or any other irreducibly complex biological system. Instead, Behe concluded that the integrated complexity of these systems pointed to intelligent design.